You could have literally the smartest artificial intelligence in the world.
Mm.
I mean, an AI that has read every book ever published, mastered quantum physics, mapped the human genome, all of it.
Right, a total superbrain.
Exactly. A model that can write a flawless symphony in like 2 seconds.
Yeah.
But if you cannot physically fit that massive digital brain onto a 10-inch piece of silicon,
It is completely useless to you.
yeah, completely useless. Welcome to today's deep dive. We spend all our time marveling at the sheer intelligence of these new models, but we almost never talk about the actual physical shelf space required to store a thought.
Which is, frankly, arguably the single most critical bottleneck in the entire tech industry right now.
Oh, totally.
Because we have this, this collective hallucination that AI is just this formless, ethereal cloud of pure knowledge. But it isn't. It is deeply, stubbornly tied to physical hardware.
Yeah, microscopic transistors on actual pieces of metal.
Exactly,
Yeah.
sitting in massive data centers.
And that tension, right, between massive intelligence and very limited physical space, that is exactly what we are looking at today. We are diving into this really fascinating piece from tech-reader.blog by Aaron Rose.
Yeah, The Secret Life of Azure, the Model Quantizer. Great piece.
It really is. And our mission today is to understand the actual physical mechanics of, well, model compression. Like, how do engineers manage to take these incredibly dense, massive AI brains and just squeeze them into tiny hardware footprints?
Without lobotomizing them in the process, which is the really hard part.
Right. So, okay, let's unpack this. Because Aaron Rose uses a really brilliant framing device to get us into the actual math of this problem.
He does, yeah. And what's fascinating here is that he completely strips away that modern, slick Silicon Valley aesthetic.
Oh, yeah, no neon lights or beanbag chairs here.
Not at all. He frames the core engineering problem through this narrative about two developers. You've got a senior engineer named Margaret and a junior engineer named Timothy.
And they're working in this grand, wood-paneled Victorian library in London.
Right, so you have this very old world setting dedicated to careful craftsmanship, but they are trying to solve absolute cutting-edge computational constraints.
And Timothy, our junior engineer, he has just hit a brick wall. He has these 3 specialized AI models, they refer to them as Phi 3 students, that he wants to spin up and actually put to work.
But he's staring at his monitor, completely blocked.
Yeah, by a C out-of-memory error. His GPU is entirely maxed out.
Which is just the nightmare screen for any machine learning engineer. I mean, you have the intelligence, but you simply do not have the memory bandwidth.
Yeah, it's full.
Timothy has already managed to shrink the scope of the intelligence. These are specialized focused models. But the physical size of the data itself is still just way too large for the hardware to hold at one time.
It's like trying to pack for a month-long international trip using only a tiny regulation-sized carry-on suitcase.
Right, a complete packing nightmare.
Yeah, you haven't packed too many items, but every single pair of socks and every single shirt is individually wrapped in like 10 layers of industrial bubble wrap.
That's a great way to put it.
You have the right items,
Yeah.
but the packaging itself is eating all your volume.
Yeah.
So if the model is simply too big for the hardware to process, my immediate instinct is that you have to make a sacrifice.
Like what?
Well, don't we just have to start deleting vocabulary? Like, don't we have to make the model inherently less smart to get it to fit into the carry-on?
Yeah, well, that is the intuitive leap most people make. If the suitcase won't close, you throw out a few shirts.
Right.
But deleting the foundational knowledge isn't the answer here. In the text, Timothy compares these AI models to incredibly heavy, dense, leather-bound books. They are brilliant, but they are simply too thick for the physical shelf space in their library.
Too many pages.
Exactly. And he asked that exact same question you just did. Do we sacrifice the vocabulary? And Margaret's answer is a hard no.
Because the problem isn't the knowledge, it's the bubble wrap.
Exactly. The root cause of the physical thickness of these models is the actual format of the data, not the breadth of the intelligence itself.
Okay, so to illustrate this, Margaret does this thing in the story. She walks up to a whiteboard with a teal marker and writes out this massive, highly specific decimal number. It's like 0.85723499103.
Just this incredibly long string.
Yeah, and then right below that huge string, she just writes 0.86.
Right. She calls that long string of digits the precision tax.
Precision tax, yeah.
She's showing Timothy that every single parameter, basically every mathematical thought inside that AI is being stored with 16 decimal places of accuracy.
And here's where it gets really interesting. Because I look at that and I think, well, precision is kind of the whole point of a computer.
You want exact answers.
Exactly. if we were just hacking off all those decimal points, aren't we fundamentally degrading the model? I mean, how is this not the equivalent of taking a stunning, pristine 4K movie and compressing it down into a pixelated, blocky GIF?
Well, if we connect this to the bigger picture, it's not a pixelated GIF at all. Margaret's analogy in the text is really helpful here. She says it's like taking a high-resolution photograph and turning it into a clean, incredibly sharp sketch.
Sketch, okay.
Yeah, you absolutely lose the microscopic, pixel-level detail, but the underlying architecture of the image, the actual reasoning and structure of the AI stays entirely intact.
Oh, right. The quote she uses is that in the real world, you don't need a microscope to read a map.
Yes, which is profoundly true for neural networks. Let's look at the actual technical transition happening here. Margaret points out that these models natively operate in a format called FP16.
Okay, let's pause there because I want to make sure we are really grasping the mechanics of this. FT16, that stands for 16-bit floating point.
Correct.
And floating point means the decimal can literally float around, right?
Yeah.
Like it allows the computer to represent incredibly tiny fractions or massively huge numbers, which gives you that microscopic 16 decimal point precision.
That's exactly right. It provides an enormous dynamic range of numbers. But Margaret wants to move the model down from FP16 to INT4.
Wait, INT4?
Yeah, that stands for 4-bit integers.
Okay, wait, going from 16 bits of floating precision down to just 4 bits. That is not a small haircut. That is a massive downgrade in how much data you are allowed to store.
It sounds drastic. Yeah.
I mean, 4 bits means 2 to the power of 4. That's 16. You are telling me they are taking this vast, infinite spectrum of microscopic floating point numbers and forcing them into a rigid grid of just 16 possible integer values.
That is exactly what weight quantization is, yes. You are mathematically snapping these highly precise decimal values to the nearest available whole number on a very limited 16-slot grid.
But how does the model not just immediately suffer from digital amnesia? You are throwing away roughly 75% of the mathematical nuance.
It seems like you are, yes.
To use an analogy, if FP16 is a digital photograph with 16 million colors, INT4 sounds like taking that exact same photo and forcing the computer to redraw it using only a standard 16-color crayon box.
Okay, that is a phenomenal analogy, and it gets to the very heart of why quantization is so brilliant.
How so?
Think about it. If you redraw a landscape with the 16-color crayon box, the sky is still going to be blue, right? The grass is still going to be green. The house is still going to look like a house.
Okay, yeah.
The semantic meaning of the image survives the compression. The neural network's ability to reason doesn't actually rely on whether a specific connection strength is 0.8572 or 0.86. It relies on the broader patterns and relationships between all those connections.
I hear that, but I have to push back here, and I'm going to channel Timothy for a second.
Go for it.
Because Timothy voices this exact same skepticism in the piece. He argues that neural networks aren't just static pictures, right? They are processes. Data flows through them layer by layer.
Right, it's sequential.
Exactly. And he points out that if you round a number like 0.857 down to a rigid integer, you introduce a tiny error. And if you do that millions of times across billions of parameters, won't those tiny rounding errors compound?
The snowball effect.
Right. A millimeter off at the very beginning of the calculation means you are miles off target by the time the AI actually generates its response. He is terrified that aggressively rounding these numbers is going to cause the model to wildly hallucinate.
And this raises an incredibly important question because Timothy's fear is highly valid.
It is.
Oh, absolutely. If you just indiscriminately round every number in a multi-billion parameter model, those microscopic shifts will absolutely compound and the model's logic will collapse. It will just start generating complete nonsense.
So, how do you compress the model into the 16-color crayon box without triggering that catastrophic snowball effect?
Well, this is where Margaret introduces the core engineering breakthrough. It's called PTQ, or post-training quantization, combined with a process called calibration.
Okay, PTQ. Let's break down the mechanics of that calibration phase, because this is where the actual magic seems to happen.
Yeah, calibration is basically the safety net against the snowball effect. Margaret draws a scale for Timothy to explain this. She shows him that engineers do not just take a machete to the model and blind round everything.
Right, they don't just hack away at it.
Exactly. Before they compress anything, they run a calibration data set through the fully trained, high-precision FP16 model.
So they are essentially giving the AI a practice test, like they pump sample queries and prompts through it.
Exactly. But they aren't looking at the AI's final answers. They are looking under the hood while the AI is thinking.
Oh, interesting.
They are watching the actual neural pathways fire. They monitor what they call the activations. By watching how the model processes the practice test, the engineers can map out exactly which specific mathematical weights are doing the heavy lifting.
And the source coins out a very specific term for these heavy lifters, right? They are called outlier weights.
Yes, outlier weights. These are the crucial, highly sensitive nodes within the network. They carry the most semantic wisdom.
You know, it makes me think of the structural integrity of building. The outlier weights are like the load-bearing walls of the AI's logic.
That's a great way to visualize it.
Yeah, because you could easily strip out the drywall or change the paint color, which is all standard everyday data, and the building is totally fine. But if you take a sledgehammer to a load-bearing wall, the entire roof caves in.
That is precisely what happens if you round an outlier weight. The model breaks and hallucinates. So the calibration process identifies these load-bearing walls.
Okay.
And once the system knows where they are, it aggressively rounds the vast majority of the normal, less important numbers down to that rigid 4-bit integer grid. But it carefully protects the outlier weights. It leaves them at a higher precision.
It literally trims the fat, but leaves the muscle completely untouched.
Exactly.
I just marvel at the elegance of that.
Yeah.
The system analyzes its own neural architecture to figure out which of its decimal points actually dictate its reasoning and which ones are just expensive bubble wrap taking up space on the GPU shelf.
And because you are doing this after the model has already been trained, hence post-training quantization, you are taking an already brilliant mind and just optimizing its physical footprint.
Right.
You get the massive reduction in size, but because you protected the outlier weights, you completely avoid the hallucination snowball effect.
Right. So we've identified the load-bearing walls, we've protected the outliers, and we've snapped the rest of the network to this super lean 4-bit grid. So what does this all mean when we bring it back to Timothy in the library?
Right, back to the CEA out-of-memory error.
Yeah, he was staring at that error, totally blocked. What did that mathematical gymnastics just buy him in terms of raw hardware capability?
The hardware payoff is staggering. Margaret runs the final numbers for him in the story. By shifting the bulk of the model from a heavy 16-bit floating point down to a lean 4-bit integer format, the total memory footprint drops by nearly 75%.
Why, 75% reclamation of physical space. That is wild.
It fundamentally alters the physical reality of the server rack. Margaret sketches out a new visual on the board for him. Instead of the rack holding one massive, heavy, leather-bound book that consumes all the available memory bandwidth and storage, that exact same space can now hold 4 incredibly slim volumes.
And the resolution of their story is just so satisfying. Armed with this compressed INT4 model, Timothy goes back to his terminal and he just hits deploy.
And it works.
It works. That glaring out-of-memory error that was blocking it, it just vanishes. He is suddenly packing the house.
Because of that 75% reduction, his hardware limitations are effectively solved. The source reveals that his 3 Phi-3 students, plus a brand new one, can now all run simultaneously.
All at the same time.
Yeah. He has a translator model, a summarizer, an archivist, and a researcher all living together on a single GPU card.
So instead of one massive genius taking up the entire room and bottlenecking the whole operation, you have 4 highly specialized experts working at the exact same desks, responding in parallel.
And this is where we see the industry-wide implication, right? This shifts the engineering paradigm entirely. For a long time, the industry was trapped in this one model, one GPU setup.
Which sounds very limiting.
It was. You had a monolithic model monopolizing an incredibly expensive piece of silicon. It was slow, and it was wildly inefficient. Quantization allows engineers to move to a multi-tenant architecture.
Multi-tenant. Like an apartment building instead of a single-family mansion.
Exactly. You are slicing up the GPU's memory. You aren't just saving space on a hard drive. You are fundamentally multiplying your computational bandwidth.
Wow.
You are getting 4 times the specialized parallel work done on the exact same physical piece of hardware, drawing the exact same amount of power.
Which brings us to this wonderful moment of realization for Timothy at the end of the post. He is sitting there watching these incredibly fast, lean responses pouring in from his 4 newly quantized models, and he summarizes the entire process beautifully.
What does he say?
He says, it's the same brain, it's just wearing a later suit.
I love that. It is the perfect distillation of model compression. You aren't changing the intelligence, you are just changing the wardrobe.
Exactly.
And Margaret caps her teal marker and leaves him with one final guiding principle. She tells him, when you master the bits, you master the scale.
When you master the bits, you master the scale. That is such a powerful takeaway because, we get so caught up in the philosophical debates about artificial intelligence, like how smart it is, what it's learning, that we forget it is a physical engineering discipline.
It's bound by the laws of physics.
Right. The real leaps forward aren't just coming from throwing more massive data centers at the problem. The progress that actually gets these tools into our hands is coming from hyper-efficient, meticulous optimization at the level of a single mathematical bit.
And that is exactly why this highly technical process matters so deeply to the end user, to you listening right now. Whether you are using an AI assistant to quickly draft an email, summarize a one-hour meeting, or parse through dense technical research, these background quantization techniques are the invisible mechanism making it happen.
It's all happening behind the scenes.
Exactly. The ability to trim the fat and map floating points to 4-bit integers is the exact reason why these massive multi-billion parameter models are fast enough, accessible enough, and cheap enough for you to use on a daily basis.
It takes the heavy, immovable, leather-bound book and turns it into a lightweight paperback you can carry literally anywhere.
Right.
Which leaves me with a final thought for you to ponder as we wrap up today's deep dive. We just explored how engineers are taking massive models and shrinking them by 75% after the fact, just by figuring out which decimal points are actually load-bearing.
So slicing it down.
Yeah. But what happens to the physical footprint of computing when we stop relying on massive billion-dollar data centers entirely? I mean, what happens when the next generation of AI is designed from the ground up to only think in these ultra-lean 4-bit sketches?
That's a fascinating question.
Right. What if the most powerful intelligence in the world is running entirely locally on the phone, sitting in your pocket right now? Thanks for joining us.
Yes.
Until next time, keep diving.